Hi everyone, and welcome to this new video about steady state analysis. And we have our design example of an RLC circuit this time. So this is our first design example, and is in fact also a filter design. So we have this following circuit. This is a passive RLC circuit, so we are stick to this circuit, and we need to design this circuit for a couple of specifications. So these are the situations, or this is the question in place, the design situation. So what we need is actually a cutoff frequency of 73 kilohertz, and the phase shift must be minus 68 degrees at 170 kilohertz. Okay, this is actually the data given here, and we have also the resistor value of 1 kilo ohm. So I need to determine the inductor value and the capacitor value. So I actually have one of the three, so I have still two unknowns. So if I know the capacitor and inductor, then I'm actually done. So what actually the handy starting point is the following. Set up your transfer function for this circuit. So your transfer function will help you in the analysis. So what is our transfer function? Which is h of s, just a name for the transfer, will be V out, output voltage divided by the V in, all in a Laplace domain, as you can see. So V out divided by V in means actually the following, using voltage divider rule, as we did also in the previous design examples of the RLC and RL and RC circuits. You look at your output voltage nodes, so what kind of impedance you are seeing, that's actually what you have here in this expression, in this ratio, divided by the complete impedance seen by the input voltage. So what I have, maybe let's first designate this as a new impedance, will helpful. So this one combined will be here designated as Z1. This will result in the following, using the voltage divider rule, Z1 divided by Z1 plus SL. SL, of course, due to the reactance of the inductor in Laplace domain. What is Z1? Z1 is, let me write it here, Z1 is the parallel combination of the R and the capacitor. So that is actually the R times 1 over SC divided by R plus 1 over SC. And if you now simplify this, you will have R divided by 1 plus RCS. Okay, I will now use this expression for Z1 in here, and then I'll simplify again so that I can use it for phase and the gain expression. So let's move on. H of S will be R divided by 1 plus RCS. And the whole term I need to divide by R divided by 1 plus RCS, and this plus as a final term SL. If I now simplify this, what can I do for this? Because it is not really useful expression in this form. I can multiply the denominator and the numerator by 1 plus RCS. We'll clean up a lot, so it will be the following: R divided by R again plus SL times 1 plus RCS. I have this expression. Again, I can simplify this, working out this parentheses. So I will have the real part and the part with the S and the part with the S squared, in this case, because it's a second order system. So you have the R divided by R plus SL plus RLCS squared. So that's actually what you get if you work out the parentheses. Alright, so that's actually the following situation. So what do we do next? Now, what you can do now is convert this in the j omega domain. That will be helpful when we do, of course, the situation for specific frequencies. So if I now convert this, so I will make S equal to j omega for this situation. This will give us the following transfer function, and I will use that, of course, in the further analysis. So h of j omega will be R divided by R plus j omega L. And I have now here an S that will be j omega squared. So j omega times j omega will be minus omega squared. So it will be actually a real part. And minus, I will place it here, so it will be minus RLC omega squared. So it will be the following: minus omega squared RLC. As you can see, we have the real part and the imaginary part already given. So the real part is R minus omega squared RLC, and the imaginary part here is just j omega L, or omega L as the length of the imaginary number. So what do we do next? Because we have a cutoff frequency and the phase shift. Let's first look at the cutoff frequency. The cutoff frequency can be, of course, of a low pass filter, of a high pass filter, or something else. Let's first look at the circuit. Is this a low pass filter or is this a high pass filter? If you, for example, consider the very low frequencies, so DC actually in the limit, it will be 0 Hertz. The capacitor will be an open for DC, and this will be short. So for DC, all of the signal at this point will be delivered to the output. So it sounds like a low pass filter at first sight. Okay, let's move on for very high frequencies, infinity. This will be open, and this will be a short. Now, if this is open, I already cannot surge current here, so that means actually there is no current flowing in the output node. So I have zero transfer from the input to output. So actually there's no gain or zero gain. That means actually there's attenuation for very high frequencies. So that sounds like a low pass filter. So it's just passing on the low frequencies. So I already can say the following: it's a low pass filter. Just looking at the circuit at some specific extreme points. So it is a low pass filter. Okay, that will mean actually the following: your low pass filter, because it's a transfer function h, will have at DC a specific value. But what is the specific value of your low pass filter for this part? So if I look at it again, for DC this will be a short, this will be an open, and the voltage here will be supplied in total to this node. So actually I have a transfer of 1. So your gain at 0, which is actually shown here, 0 radians per second or 0 hertz, doesn't matter, is just 1. And the definition of the cutoff frequency, because I am heading to the cutoff frequency using this definition, the cutoff frequency means actually the following: what is the gain of your DC value, or I mean your DC at your DC, so that means actually in this case 1, and multiply that by 1 over square root of 2, that will define your cutoff frequency. So I have to do following. For a cutoff frequency definition, your frequency, cutoff frequency for your system, amplitude of that, must be equal to 1 over the square root times the low frequency gain. This for, of course, for the low pass filter valid. For the high pass filter, I have to do 1 over the square root of 2 times the high frequency gain. That's just actually what you have for a high pass filter. So I know this is just 1. It can be other numbers, so be careful what you have. This is, for example, there is a resistor here. Then I have a voltage division. It can be, of course, maybe less than this one. Okay, so we have this. That means actually 1 over square root of 2 times 1 will be, of course, again 1 over square root of 2 times 1, which is just 1 over square root of 2. This is very important, so I know actually at this frequency my gain will be 1 over square root of 2. That's actually the definition of this is the definition of the cutoff frequency. This is very important. So I have at this frequency, which is this one, so omega, let me write it down, for omega, cutoff is 2 pi cutoff, and cutoff f of c will be here 73 kilohertz, will be 146 times 10 to the power 3 pi radians per second. So we will work with this number instead of 73,000 hertz. Okay, let's move on to the next part. I will now set up the gain and the phase expressions using this expression for the transfer function. So let's move up all to the right. So I have the phase and the gain. So the gain and the phase. And these are required because I have also both of them. So I have the gain and the phase given already in the design. So it is handy to already set them up. So what is actually the gain expression? So the amplitude or the magnitude will be R divided by, if I take the real and imaginary parts here, so let me write it down maybe in a different form. So this will be R divided by, and I will take all the real parts, R minus omega squared RLC. It's just a complete real part, and then plus J omega L. That's for the imaginary part. Alright, so I will square this in total, plus I will square omega L in total, and I will take the square root of that. It will be actually the following. So we have the R minus omega squared RLC in total squared plus omega L in total squared, and of course the square root of that. That's actually the length of this one. Alright, that's the gain. That's just the expression for the gain. Alright, for the phase, I will take the phase contribution of this part and minus the phase contribution of this part. This is actually just using here again arctangent, so the imaginary part divided by the real part. And for this one, I have actually a phase contribution of 0 because it's just pure real element. So we have the following: phi of omega will be 0 minus arctangent of the real part, which is omega L, divided by R minus omega squared RLC. That's all. That's fine. Okay, what do we do next? Okay, we know what the R is, which is 1000. We can already substitute that. We know what our cutoff frequency is. We already have given. We know what our phase is at a specific frequency. So all of them can be used to determine the required value for the inductor and the capacitor. As you can see, we have two equations and two unknowns. Why? Because the omega is known for specific conditions, and the R is known for all conditions. So you can already use that. So let's first start with the cutoff frequency. So let's move on with the cutoff frequency. So if I now write down the following, it will be J 146,000 pi, an absolute value of that. I will use this expression, substitute for R 1000, omega will be this, and I will express this, of course, equal to 1 over square root of 3, 1 over square root of 2, which is actually shown here. This is actually the expression again, yeah, because it is the cutoff frequency. So what do I have? I have the following: 1000 on top, and I have a very big factor, so it'll be 1000 minus the cutoff frequency will be squared times 1000 times LC, and the whole quantity, I will make it in brackets to make sure it's correct. That's actually the situation for the first real part, and the imaginary part will be also in the same fashion. So I will have the omega substituted, and the L is unknown at this point, and this is equal to 1 over square root of 2. As you can see, this is just the expression here. Just substitute the value of the omega. Omega is omega cutoff, and the R is 1000. What you see is we have still an equation with two unknowns, so it is actually at this point unsolvable. So what we have is we need this also, and we have a situation for the phase. So the phase is actually the following: at this frequency, of course, we have to multiply this by 2 pi with 2 pi. The phase must be minus 68 degrees. So I will use it also. So I will do that the following. I will have the phase of 2 pi times 170,000 will be, you can also write it like this, so 2 pi times 17 times 10 to the power 4, which is actually the specific frequency which we have now, must be equal to minus 68 degrees, which is actually shown there. So if I now substitute this value in here, and also the R, what do I have? I have the following. Minus arctangent, and then this can be simplified to, of course, 34. So that can be 34 times 10 to the power 4 pi divided by times L, of course, divided by 1000 minus 34 times 10 to the power 4 pi whole squared times 10 to the power 3, which is the R, and times LC, and that must be equal to minus 68 degrees. As you can see, I have this R, this omega here squared, I have the R here, L and C are unknown, and also the L here is unknown. Okay, this is actually the expression for the phase. As you can see, again we have two unknowns, but we have now two equations, so I can now number them, because this is just number 1, and this is just number 2. So I have two equations already. What do I do next? What can I do next? Okay, I can now rewrite this equation, equation number 1, so that I have this in a more simplified form, so I can use it later on. Or I can start with this one, it doesn't matter. What I want is the following. I will like to have an expression for L times C, just a product, which is something in terms of L or in terms of C, and I will then substitute that in the other expression. So for example, if I work this out, and I have the LC is equal to something in terms of the L and other numbers, I will then take that expression, number 3, and substitute for example in here, because I have an LC here. Then I have an expression, this magic expression will be only in terms of the element L. And then I can solve it because there is only one unknown. So that's actually the whole business. I can start here, doesn't matter, I can start here. So let's start here, doesn't matter. So what do I do is the following. I will square left and right side. I will then do 1000 divided by a half, because if you square this it will be a 0.5. Then I have this expression in the square root will be equal to 2 times 10 to the power 6, because you have also squared there. So that's actually the step what I do here. So let's write it down. So I have the following. I have the 10 to the power 3 minus the cutoff frequency whole squared times the 1000 LC, this whole part squared, and the second part also, just take over everything what we have there, also squared, and this will be equal to 2 times 10 to the power 6. I will also number this, will be equation number 3. Okay, I will now move to the phase, so I will have this expression. I will now move to the phase, and I will set up an equation such that I have LC is equal to, in terms of L, and other numbers, but no C, so actually they're just a product. So if I now do that, I will take the minus sign left and right away, so this times minus sign. I will take the arctangent left or right side, so that I mean the tangent, so it will be tangent of 68 degrees. Now, shuffling around, you will have the following. You will have, let me continue with black, will be much better to see. So 34 times 10 to the power 4 pi L divided by 1000 minus, again, the same frequency, squared times 1000 LC will be tangent of 68 degrees. Okay, that's actually our situation now. If I now move on and then express what I did, what I just mentioned, this part divided by a tangent of 68 degrees, and then shuffling around such that I have an expression in LC is equal to the rest. So I have the following. I can just continue 10 to the power 3 minus, again, the same expression for the frequency. Just take over everything what you have, step by step, which will be this, just a number, times L, divided by this is also a number. So I will have the following. If you do the math here correctly, you will have 4, 3, 1, 5, 5, 7 times L. That's actually the answer for this 34,000 pi divided by tangent of 68 degrees will be this number times L, of course. If you now rewrite this, what you have is the following. You will have LC in a final form 1000 minus 431,557 times the L divided by 1000 times the frequency what we have there, and pi completely squared. This is actually the situation. So I find out, denote this as a new equation number 4. I have now a very nice situation, because I have now equation number 4, which I have actually wanted already. This is now LC, and I can now substitute that in this equation number 3. So I will take this completely and place it in here. It will be, of course, a huge equation, but then I have only one unknown. So we have to do something. Alright, so let's move on. As you can see, it is a little bit challenging calculation, but we will solve it. So substitution, or substitute, it's also better. So substitute 4 in 3. What do we have? So what you have following, 10 to the power 3 minus the frequency which you see there, times 1000 times this term. Yeah, I will just write down, because it is 1000 minus 431,557 L divided by 1000 times 3, 4 times 10 to the power 4 pi squared. That's all. And then I continue. So what do I have? I have, of course, this in complete form, and then the complete situation squared. So I have this squared plus this second part, so 146,000 pi times L squared will be 2 million. So we have a very huge equation, but what we have is very nice, because there is only one unknown, which is actually L. So I can just solve this. Of course, if you can solve this using just a solver, is much handier than do it with your hand. But it is already an equation with just one unknown. So this is doable. So what we have, if you solve this, solving, which gives you L is equal to 0.0022 henries, will be thus 2.2 millihenries. Okay, I'm done with one of the unknowns. The next one is the capacitor C. Now I can use the following expression, just a little bit of rewriting it, and I can calculate C, because how can I now calculate C? I know L, and if I rewrite this, what do I have? Let me show this. So if I now rewrite this, C will be equal to 1000 minus 431,557 L, but L is 0.0022. So we give it in the parentheses. That's actually what we have determined a couple of seconds ago. So I have now this, and this will be 1000 times the frequency, 34 times 10 to the power 4 pi squared, and I will divide this also by L, because if I divide this term by L, I will have the capacitor, just an expression for the capacitor. So I will have also 0.0022. I will give it also in the parentheses here expression. So if I do the math here, you will have 2 times 10 to the power minus 11, very close to that value. In farads, it will be, of course, if you do that in picofarads, it will be 20. And I'm done. This is quite a lot of work, as you can see, for the inductor and the capacitor value, but this is actually the way we can solve this quite challenging design example. As you can see, this is just not only a cutoff frequency, but also a phase shift for a specific frequency. So if I a little bit zoom out, you can see the whole procedure in more detail. That's actually what we did. So we started with the impedance first determining, and then the ratio of that, determining the Laplace form of the transfer function, then going to the j omega domain, then gain and phase, always important, and substituting and giving values, and we have the expressions for the gain and the phase also using the values we have here, and then we have calculated the inductor and the capacitor, since we have 2 equations and 2 nodes. And that's actually the whole design example for this RLC circuit design. Again, this is in fact a filter design, and we have now designed the circuit according to specifications.